Okay, first of all, I thank you very much, Lucia and Matteo, for inviting me to this exciting workshop and also for giving me the chance to meet so many Italian colleagues I didn't know that are doing a lot of good science. So thanks a lot, really. So the subject I've chosen for this talk is molecular hydrogen metrology, because this was a subject that we tackled with much enthusiasm in Lecco, because this is where my laboratory are actually located. This is the result of quite a big cooperation that includes also theoreticians from the Nicolaus Copernicus University and from CNRS Rennes. But the major work has been done here in Lecco, and I want to acknowledge the great contribution that Marco Lamperti, who is now here, gave to this subject when he was postdoc in my group. So before moving to hydrogen, I just spent a slide in saying that we are carrying out essentially two major research lines in Lecco. The one is related to a Pathfinder project I'm coordinating. It is devoted to the development of an ultra-fast holographic microscopy platform for cancer diagnostics that aims essentially at providing hyperspectral images of a biopsy in the fingerprint region, so between 5 and 10 micron wavelength, but with the same spatial resolution that you may get with visible light, so subcellular resolution. So this is one thing that we started working on a few years ago with this project, but the most historical research line in Lecco has been the use of this wonderful tool, which is the optical frequency comb awarded by the Nobel Prize for Physics in 2005, essentially for two kinds of applications: sensing, trace gas sensing. So thanks to the ability with this comb to track many absorption features at once, but also metrology. And it is within this metrology area that falls actually today's subject. So why molecular hydrogen? Well, first of all, because it is a very fascinating molecule. As you know, it is the most diffused molecule within the universe. Almost 75% of matter is made of hydrogen. You can find it in stars, you can find it in gas giants such as Jupiter, Saturn. And so, of course, acquiring good accurate laboratory data for hydrogen makes much sense for this astrophysical data. The other element of interest for fundamental science is the fact that hydrogen is the simplest molecule you may have. And so it is an ideal benchmark system to perform very accurate calculation of the energy levels. And so it is an excellent testbed for comparing theory and experiments. And since the invention of optical frequency combs, this kind of intersection between theory and experiments in the frequency domain can be done very well, thanks to the fact that now optical frequencies can be calibrated against our primary radio time and frequency reference. So you may test molecular quantum electrodynamic models. You may also go further and try and determine fundamental constants of physics, such as the Haber-Fine constant or the proton-to-electron mass ratio, but this requires a level of accuracy also from the theoretical side that is not yet available. So which transitions and which energies are we talking about? We are referring to fundamental vibrational transitions, so transitions that link the ground vibrational state to the first excited vibrational state. But the discussion we will have covers also the chance to address purely rotational transition that is within the ground vibrational state. So as I told you, a big trigger to this activity grew up because of good calculation. The first milestone was this physical review letters papers in 2013, where the groups of Comas and Pakulski in Warsaw and the group of Wim Ubachs in Amsterdam published this line list of fundamental vibration frequencies of a molecular hydrogen with an unprecedented uncertainty of about 10 megas. This uncertainty was then improved by almost a factor of 10 a few years later. And this actually triggered a kind of race among the experimentalists, such a way to catch up these levels and possibly do some meaningful comparison between theory and experiments. In more recent years, theoreticians focus also on upper fine structures, reaching uncertainty levels that are even higher. But from the experimental point of view, hydrogen poses some challenges. The very fact is that due to the fact that it is a nuclear diatomic molecule, doesn't have an electric dipole moment, and so it is a very weak absorber, since absorption lines are mediated by very weak electric quadrupole moment. And so how to address this issue? Typically, what people in the field do is to fit hydrogen into an optical cavity surrounded by two mirrors with very high reflectivity, because one can easily show that in such a case, the effective interaction length between radiation and matter is enhanced essentially by the finesse of the cavity. When we started our idea of using a nonlinear spectroscopy to address hydrogen metrology, one of the things that we were more scared about this more traditional approach was the fact that it is hardly scalable to the mid-infrared due to the poor quality of lasers, mirrors, detectors, and so on. Another important motivation for our development is that if we were looking at the time at the only concalibrated measurement of a fundamental vibration transition of H2, the experimental value was suffering from an uncertainty of about 6 megahertz, which is pretty large as compared to the more recent theoretical findings. And so that's why we decided to go our own way and try to measure accurately these line frequencies using a nonlinear approach, stimulated Raman scatter. Why SRS? First of all, because these quadruple lines are allowed in the Raman regime. The second important thing is that both vibrational transition and purely rotational transitions can be addressed using near-infrared lasers. So you don't need IR technology or far-infrared technology. And intriguingly, no calibration attempt was done so far with optical frequency console. Produce the calibration of the frequency axis in this nonlinear spectroscopy mesh. So one might argue whether we have been the first doing this, or at least using SRS for hydrogen, but it was not the case, because in the 80s and the 90s, using both CW lasers and nanosecond lasers, a lot of research has been done for the study of pressure broadening and shifting parameters of hydrogen in this nonlinear region, but before the invention of the frequency code. So here is a very brief outline of what I'm talking about in a few minutes. So I give you a few basics of stimulated Raman scattering, and I will present then this spectrometer that we have developed around this idea of using SRS. The measurements that we have done concern this Q1 line, which is the most famous stretching mode of hydrogen. It lies at the 4,155 of numbers. And actually, I will discuss some pitfalls that may happen when you want to be very accurate, but you are forced to measure your transition energies in a colliding environment. And then I will draw some conclusions. Okay, what is stimulated Raman scattering? It is a third-order nonlinear process that can be regarded as a stimulated emission from a virtual level. In order to drive this process, what you need is two lasers at two frequencies, the so-called pump and Stokes laser frequencies. And quite nicely, if you bring the frequency difference between these two frequencies to be resonant with the frequency of the transition that you want to eventually excite, you can close this energy photon diagram loop quite easily and assist to annihilation of pump photons, stimulated emission of Stokes photons. And this macroscopically results in the fact that your Stokes laser intensity grows up, your pump intensity gets depleted, and so you can measure essentially this effect, either addressing SRG, stimulated Raman gain, or stimulated Raman loss. In our case, we experimentally measure stimulated Raman loss, which is defined as the relative change of the pump intensity. And so in order to do the measurements, you have just to scan the frequency difference between pump and Stokes lasers against your target transition and acquire a spectrum. So before starting this activity, we wanted to have an idea of how much SRL we could have in a, let's say, measurement in standard conditions. So the estimated Raman loss is a parameter that is proportional to the K3 of the medium, which is the quantity that entails the frequency dependence. But interestingly, it is proportional to the Stokes laser intensity, to the interaction length, without any phase matching term. There is a degeneracy in this process that makes it independent on phase matching issues, such as, for example, you have in cars coherent distortion scattering. And so in order to have sufficiently SRL in a gas phase, it is important to use a multipath cell to have a high power Stokes lasers. And our SRL signal estimation performed at a pressure of 1 bar for this 10Q1 line, assuming a Stokes laser power of 5 watts and then multipath cell as long as 30 meters, was the following: 5 10 to the minus 4. So it is a tiny signal, yet not that tiny if you compare it with the shot noise limit of a 1 milliwatt pump at 740 nanometer, which is actually the laser wavelength that we used. So the shot noise limit is at the level of 3 parts of 10 to the 8 per square root of Hertz, which means that in principle, if you reach shot noise limited detection, you may think in these thermodynamic conditions to measure this SRL with a SNR of about 10 to the 4 per spectral point per second. This is the layout, the general layout of the spectrometer that we built. It is constituted by 2 CW lasers at wavelengths that give us the frequency difference we were targeting, that is 4,155 watt numbers. Then these 2 lasers that are CW in order to have sufficient spectral resolution, because I remember you that we are in a gas phase, so the lines we are investigating are pretty narrow. The 2 lasers are combined and then sent to a multipath cell where interaction with hydrogen occurs. Then the pump laser beam is extracted out for SRL measurement. And since we are willing to measure a very tiny signal on top of a background, we recur to a modulation transfer detection technique in such a way that we intensity modulate the Stokes lasers, and we measure the modulation transfers to the pump with a low-key amplifier at high frequency. We have several active controls ongoing for temperature and pressure, because we want to average our results for a sufficiently long amount. We want to do measurements over long times in such a way to average multiple spectra, so we need stable thermodynamic conditions. At some point, we realized that we had also to implement an active control of the alignment between the 2 beams, because we found out that any, let's say, angular offset between these 2 beams due to trivial beam pointing instabilities was impacting on the accuracy of our measure. For the comb referencing of these 2 lasers, we started from a niobium fiber laser that, thanks to a supercontinuum fiber, was covering this 1100, 2200 nanometer range. And in order to access the 2 wavelengths we were needing for the referencing, we employed the 2 second harmonic generation schemes in such a way to generate these 2 frequency combs, where that give us the chance essentially to measure the position of these 2 lasers by acquiring the bit nodes between the 2 lasers themselves and the nearest mode of the comb. Quite interestingly, in this scheme, you can avoid to stabilize the carrier envelope offset frequency of the comb that corresponds to the actual position of the comb. It is not the spacing, it's just the absolute position, because you see that these comb modes share the same offset. And so what it happens is that if you measure the bit nodes, which are the difference between the 2 laser frequencies and the nearest mode comb frequencies, it is easy to show that you can access the frequency detuning between pump and stokes, provided that the repetition frequency of the comb is known, that is, the spacing of the comb is known, and the bit note frequencies are suitably measured. And all this happens so without any need for stabilizing this. So I just give you an additional detail on the measurement scheme. So in our case, the repetition frequency of the comb was set to 100 megahertz, and this was referenced to a GPS disciplined frequency reference. So this was an absolute 100 megahertz value, and this was fixing the spacing between the comb. Then the pump laser at 740 nanometer was locked to the nearest comb mode with a servo loop, so it was lying at a known offset from the nearest comb mode. And then for the Stokes lasers, actually the Stokes laser was scanned, okay, back and forth in order to acquire multiple spectra to be then averaged. And in order to calibrate the position of the Stokes laser while scanning across the comb, what we did is simply to use a fast digitizer equipped with an onboard FPGA that essentially was digitizing this this beating note between laser and comb while scanning. And if you low pass this beat note at 50 megahertz, half the comb rep rate, the kind of bit note behavior that you measure is this sawtooth behavior. Essentially, when you have a positive loop, it means that the Stokes laser is getting away from the nearest comb mode. When you have the negative loop, you are approaching the other one. And so by unfolding this sawtooth, you can actually refer your frequency axis perfectly to the comb and get calibration of your SRL spectra. So this is an example of spectra of pure hydrogen acquired at different pressures from about 50 millibar to 4 bar, so across a 2 decades larger range. So a first feature that is clear is a very strong pressure shift. You see, it is a pressure shift which is as high as 700 megahertz, while we are aiming at uncertainties possibly below 1 megahertz. So one of the crucial things of this kind of metrology is to have a good model to extrapolate the line center to zero pressure, because the line center frequency we are interested in is the line center frequency of the isolated molecule. But we are forced to measure hydrogen in a colliding environment that provides this shift. Another striking feature is the fact that in hydrogen, if you look at the line width at low pressure, where the broadening is dominated by Doppler broadening, you find a much larger line width than high pressure. This is the phenomenon known as Dickey narrowing. Essentially, collisions at high pressure in hydrogen lead to a modification of the Maxwell distribution of velocities. This distribution of velocities gets more peaky, and so the Doppler broadening is somehow quenched. And what you observe at high pressure is essentially a collision mode. So what was the model that we used to reach a decently high accuracy? Well, we recorded to this beta-corrected Harman-Tran profile. It is known in the literature as being the most accurate analytical profile that you can use to simulate several collisional effects of molecules. So it is a profile that is characterized by many parameters, all having a clear physical meaning. So nu zero is, of course, the center frequency we are interested in, and it is the center frequency of the Ampere curve line. Then what you may find here are parameters such as the Doppler width, the collisional broadening and shifting upon speed averaging. These are quadratic corrections to this broadening and shifted introduced by collisions that are speed dependent. Then there is this parameter that accounts for the Dickey narrowing, and this is a correlation between velocity and phase-changing collisions. Finally, there is also this beta variant, which is nothing but an adaptation of this HTP for H2. Anyway, when you have so many parameters to be fitted, of course, the risk of suffering from the many correlation between these parameters and infer some wrong value is very high. So that's the reason why we involved in our cooperation some scientists, in particular the group of Piotr Chiswo from the Nicolaus Copernicus University in Turin. Essentially, they were able, starting from potential energy surfaces of the hydrogen molecule, to calculate the expected line shape due to collisions, solving quantum scattering issues. And by these calculations, we were able essentially to take some of these parameters fixed and reduce our fitting to few parameters. So these are our spectra in a normalized scale. And this is what we get by using this apparently accurate HTP profile in different conditions. So this dot, for example, refers to the difference between the retrieved line center and the reference value from theory when all the spectra, that is the entire multi-pressure dataset, is used for the fitting. And you see that we have quite a big deviation as compared to this expected value. But even more critically, if you restrict the fit to spectra up to 1 bar, we see it and we determine a different line center. And things go even further if we reduce our data set to the first 3 spectra datasets at the lowest pressure. What does it mean? It means, first of all, that our model is not working well, for sure, at high pressure, because a good model would allow us to retrieve a unique value of line center for the unperturbed model. But the very question is, are we stuck with this issue, and so we can't actually infer any meaningful value for our line center? And so one of the good ideas that we had is to try and compute this kind of trajectories by repeating the fitting upon changing one of the parameters of the fitting. In this case, it is the linear line shift within its confidence interval. So this is the line shift varied by plus minus 10%. You see that if we use all the pressure that we had, so all the spectra at all the pressures, we can get highly scattered bands. But as long as we restrict the fitting to the lowest pressure examples, all these trajectories do converge. And we can also extrapolate by simple parabolic fitting of the latest points in this trajectory a final value for the zero pressure line center. And we could also estimate our uncertainties, our systematic uncertainties due to the line shape model by comparing, just looking at the offset between these extrapolations. And that is the final uncertainty budget that we got. We were limited by, let's say, statistical noise of the measurement to about 200 kilos, and the line shape model was contributing to a type B uncertainty, that it was a systematic error by 200 kilos, so bringing the final accuracy to 300 kilos. That was a good result. That was a good result because now in the panel I showed you before, we could finally add a new dot, this experiment, yellow, which was having an error bar comparable, even better, I would say, with the best theoretical estimation for that line. So, but let's try and put this in a bigger scenario. This is the result of our measurement. So in this graph, the zero value on the vertical scale is, let's say, the theoretical calculation of the line center. And all these dots are experimental values obtained for transitions that belong to different isotopes of H2 and even different row vibrational bands. So the green dots refer to the fundamental row vibrational bands, the blue dots to the overtone bands. So you see many measurements in the literature with optical cavities, also with our techniques, different lines. And this red shaded area corresponds to the expected accuracy from theory. Whereas for experiments, you can look at the error bar. So you can see that there is definitely a systematic shift between experiments and theory because all experimental values are in excess of theory. So definitely this is not yet the proof that quantum electrodynamics should be changed, but it is actually the problem of wrong approximations in those calculations. And this was further confirmed by even more recent, let's say, determinations. Our determination was done in 2022. The group of Wim Ubachs, for example, recently managed on this S0 line of the Overton band to have an extremely high accuracy thanks to a sub-Doppler measurement. But you see that in such a case, the discrepancy is about 3 sigma, and it is dominated by theory. So in this competition between theory and experiments, there is room for improvement. So I get to the conclusion. I think, you enjoyed this journey through the first calibrated coherent Raman spectroscopy into the application of this coherent Raman spectrometer to H2. Actually, this spectrometer that has been applied so far for H2 can become a very interesting tool in reality for many other quadrupole lines. And with minor changes, our setup can be tuned to any line from 50 to 5,000 with numbers, also reaching rotational lines. What I also showed you is that some enhancement of the signal to noise ratio would be highly valuable to decrease any systematics related to pressure and to a non-perfect modeling. And it is along this direction that we are now trying to evolve our spectrometer from the current layout where a multipass cell, an area of multipass cell is used. Now this kind of cells work in an almost confocal configuration and provide beam radius of about 265 micron, to a more fancy environment called hollow core fiber, where the beam radius is squeezed by a factor of 10, and so the signal might be enhanced by a factor of about 100. This would allow to use 100x lower pressures and reach also a regime where collisions are dominated by the walls of the fiber and no longer by H2-H2 collisions, possibly leading to simpler models for more accurate extrapolations. And I conclude by at least acknowledging and thanking the contributions from the Italian part of the team. This is an Italian workshop, so Davide Gatti, with the historical cooperator in my group, Francesco Basso-Basset, who is here in the audience and recently reached the group. He comes from La Sapienza Roma and has a quantum technology background, but we are merging the two things. Piotr Borges comes from Poland and is bringing the know-how on optical fibers, hollow core fibers, and of course Marco now at Insubria. Then thanks a lot for your attention. So.